In last class we discussed on what is solid angle and intensity of radiation. Today we are discussing on the Kirchhoff law and the heat exchange by radiation between the two bodies. The first concept that we are discussing today is the Kirchhoff law. The Kirchhoff law states that at any temperature, the ratio of total emissive power to the total absorptivity alpha is constant for all substances which are in thermal equilibrium with their environment. That means whatever may be the material, whatever may be the substance, at a particular temperature, the ratio of the total emissive power to the absorptivity, that means the ratio of the energy emitted by the body to the amount of energy absorbed by the body, this ratio remains constant for all the substances. The value may vary, the amount of energy emitted by the body and absorbed by the body may vary, but the ratio of the total emissive power to absorptivity alpha remains constant for all the substances. This ratio remains constant for all the substances when they are at same temperature. Kirchhoff law states that at any particular temperature, the ratio of total emissive power to the absorptivity alpha is constant for all the substances. This ratio remains constant at a particular temperature which are in thermal equilibrium with their environment. That means irrespective of the material, when they are at the same temperature, the ratio of emissive power, that means the amount of energy emitted by the body to the absorptivity is nothing but the amount of energy absorbed by the body, this ratio, the E by alpha, remains constant for all the substances. Okay, to prove this, let us consider a small gray body. Okay, a gray body is one, as we said earlier, its thermal properties such as absorptivity, transmittivity and other things doesn't changes with the temperature, it remains the same. Let us consider a small gray body having area capital A1, its emissivity value is epsilon and temperature epsilon suffix 1 and temperature T suffix 1 or T, capital T. We considered a small gray body having area A1, capital A1, emissivity epsilon 1, epsilon and the temperature T, which is located inside a black body. Inside a black body enclosure. It is completely enclosed. This gray body is completely enclosed by a gray body. And this black body is also at the same temperature called T. Both gray body and black body are at the same temperature. As we know, the black body emits more radiations and absorbs more radiations than other bodies even at the same temperature. Its emissivity value is 1, whereas the emissivity value lies between 0 to 1 for other bodies. For a white body, the emissivity value is 0. And for other bodies, the emissivity value lies between 0 to 1. From Stefan-Boltzmann Law, the radiation emitted by the black body is given by sigma into A into T to the power of 4. Let us consider area of the black body as 1 meter square, then the amount of radiation emitted by the black body is given by E suffix B equals sigma into T to the power of 4. From the figure you can see the outer layer is completely insulated, therefore the radiation emitted by the black body completely falls on the grey body. Therefore, now the radiation received by the grey body is equal to the energy emitted by the black body, since they are at the same temperature, and is given by E suffix b equals sigma into T to the power of 4. But it is a grey body. It doesn't absorb all the radiation falls on it. Only black body receives all the radiation. Therefore, radiation absorbed by the grey body is given by alpha 1, alpha suffix 1 into sigma T to the power of 4, where alpha 1 is absorptivity of the grey body. Therefore, the radiation absorbed by the grey body is given by alpha 1 into sigma into T to the power of 4, or alpha 1 into E suffix b. For the grey body to be in equilibrium, all the radiation absorbed by the grey body must be equal to radiation emitted by the grey body. We already said it is at a constant temperature T. If it has to be in constant temperature T, the amount of radiation, it should be, that means it is at a constant temperature T means it is at thermal equilibrium. For equilibrium, the amount of radiation absorbed must be equal to energy emitted by the body. Therefore, E suffix 1 gives the emissive power of the grey body, and this must be equal to the amount of radiation absorbed by the grey body for equilibrium. From this, we can write E suffix b equals E1 by alpha suffix 1. Okay, E suffix b equals E1 by alpha 1. In general, we can write E suffix b. That means emissive power of black body equals emissive power of a particular body divided by absorptivity of that particular body. And we can write in general E1 by alpha 1, E2 by alpha 2, E3 by alpha 3. Also, from the definition of emissivity, we were having, what is emissivity? It is the emissive power of any body to the emissive power of black body. From the definition of emissive power, we can write E suffix b equals E1 by epsilon, where epsilon is emissivity of the body 1 or the grey body. We are having equation number 1 where E suffix b equals E1 by alpha 1, where alpha 1 is absorptivity and epsilon is emissivity. From 1 and 2 we can write emissivity is equals to absorptivity. Okay, that means at a particular temperature the amount of radiation emitted by the body is equal to the absorptivity. This is what the Kirchhoff law states. The ratio of total emissive power to the absorptivity alpha is constant. Whatever may be the body at a particular temperature, when they are at the same temperature, the ratio remains the same. The ratio remains the same. When they are in thermal equilibrium, the ratio remains the same. The ratio of emissive power to the absorptivity remains the same, and when they are at particular temperature, the emissivity value is equal to absorptivity. Okay, this is what we have to prove. The next is the radiation exchange between the black bodies separated by a non-absorbing medium. Here we are discussing on how the exchange of radiation takes place between the two bodies. Between the two bodies when they are separated by a non-absorbing medium. That means the medium which separates them doesn't absorb any radiation. Okay, To prove this, let us consider the heat exchange between the two elementary areas dA1 and dA2 of black radiating bodies. Here there are two bodies, both are black bodies, A1 and A2. We are not considering the entire area of those two bodies. Instead of considering in the entire areas, we are considering a small elementary area dA1 of A1 and dA2 of A2. Then we are calculating the amount of radiation emitted by the small bodies dA1 and dA2. Then by integrating we can find the amount of radiation emitted by A1. We considered small elementary areas dA1 of A1 and dA2 of A2, which are at temperature T1 and T2 respectively. First we considered the radiation heat exchange between the two elementary areas dA1 of A1, dA2 of A2, which are at temperature T1 and T2. These two elementary areas are at a distance r, small r. This dA1 and dA2 are at a distance r. And if you draw the normals to these elementary areas, these normals are making an angle θ1 and θ2. Makes an angle θ1 and θ2. θ1 is the angle made by the normal drawn to the dA1 in the direction of dA2. Similarly, dA2 is the θ2 is the angle made by the normal drawn at dA2 with respect to dA1. A straight line is drawn between dA1 and dA2 to measure the distance, and if you draw the normal, this normals making an angle θ1 and θ2 with respect to dA1 and dA2. Let us consider dW1 be the solid angle subtended by dA2 at dA1 and dW2 be the solid angle subtended at dA2 by dA1. By dA1. I already said dW1 is the solid angle subtended at dA1 by dA2, and dW2 be the solid angle subtended at dA2 by dA1. Then dW1 and dW2 are given by the equation. What is dW1? It is the solid angle subtended at dA1 by dA2. That means when you view from dA1, dA2 makes an solid angle dW1. When you view from dA1 at an angle θ1, it looks like an diminished object. I already said solid angle is given by the area divided by the surface area surrounded by a conical surface divided by the distance r square. We already defined the solid angle. Therefore, that solid angle dW1, which is subtended at dA1 by dA2, is given by dA2 cos θ2, because it is a diminished image as seen from dA1. dA2 cos, it is not in, because I said dW1 is the solid angle subtended at dA1 by dA2. When you view 2 from dA1, it is a diminished object, and this diminished object is given by dA2 cos theta divided by r square. Similarly, dW2 is the solid angle subtended at dA2 by dA1. As seen from dA2, dA1 is a diminished object, and this diminished image is given by dA1 into cos theta 1 divided by r square. Okay, these are the solid angles now subtended at dA1 and dA2. Next, the rate of radiant energy leaving dA1 and striking on dA2 is given by dQ12. It is the amount of radiation emitted by the surface dA1 and falling on the surface dA2. From the definition of intensity of radiation, it is the amount of radiation emitted by the body per unit area and per unit solid angle. I suffix B1 equals dQ12 by dA1 cos theta 1 into dW1. And the rate where dQ12 is the amount of radiation emitted by the body 1, and it is given by, from the definition of intensity of radiation, I suffix B1, where I suffix B1 is the intensity of radiation emitted by the body 1 into dA1 cos theta 1. dQ12 represents the amount of radiation emitted by the body 1 and falling on the body 2. I suffix B1 represents the intensity of radiation. dA1 cos theta 1 represents the area as seen from dA2 because it is falling on the body 2, and dW1 gives the solid angle subtended at the area 1. Okay, now substitute the value of dW1, which we already defined in the last slide. Now we get dQ12 equals I suffix B1 into dA1 into dA2, dA1 cos theta 1 into dW1 is given by dA2 cos theta 2 by r square. We substituted the value of solid angle 1 dW1 in the equation, and we got dQ12 equals IB1 into dA1 into dA2 cos theta 1 into cos theta 2 by r square. This equation number 1 gives the amount of radiation emitted by the body 1 and which falling on the body 2. Similarly, body 2 is also a black body. It is also emitting some radiations, and the radiation emitted by the body 2 is falling on the body 1. The amount of radiation emitted leaving the body 2 and striking the body 1 is given by dQ21 equals IB2, where IB2 gives the intensity of radiation of body 2 into dA1 dA2 cos theta 1 into cos theta 2 by r square. Equation number 2 gives the rate of radiant energy leaving the surface 2 and striking the surface 1. Both the surfaces, both body 1 and body 2 are the black surfaces. Both the surfaces emitting radiation, and the radiation emitted by both the surfaces falling on other bodies. Therefore, the net exchange of heat between the two bodies can be given by subtracting the equation 1 and 2. In equation 1 and 2, dA1 dA2 cos theta 1 cos theta 2 by r square is common. Taking that outside, we will get on the right side dA1 dA2 into cos theta 1 into cos theta 2 by r square into I suffix b1 minus I suffix b2. But in the last class we proved that the emissive power of a black body is equal to pi times its intensity of radiation. E suffix b equals pi into I. Substituting that, we will get dq12 equals dq12 minus dq21. Don't confuse. dq12 represents the net rate of heat exchange between dA1 and dA2. dq1 suffix 2 represents the amount of radiation emitted by the body 1 and falling on the body 2. dq suffix 2 minus 1, 2 semicolon 1 represents the radiation emitted by the body 2 and falling on the body 1. Don't get confused. Again I am repeating. dq12 represents the radiation heat exchange between the body 1 and 2. dq suffix 1 semicolon 2 represents the radiation emitted by the body 1 and falling on the body 2. dq2 semicolon 1 represents the radiation emitted by the body 2 and falling on the body 1. Okay, we substituted the value of emissive power in terms of pi into I in the equation, and we got dA1 into dA2 cos theta 1 into cos theta 2 E suffix b1 minus E suffix b2 divided by pi r square. But from Stefan-Boltzmann law we are having E suffix b equals sigma into t to the power of 4. We are having, from the definition of Stefan-Boltzmann law, we are having for a black body, emissive power of a black body is directly proportional to 4th power of absolute temperature. E suffix b equals sigma into t to the power of 4. Substituting that value, we will get dq12 equals dq1 semicolon 2 minus dq2 semicolon 1 equals sigma. We got that outside. Sigma into, which is common, dA1 dA2 cos theta 1 into cos theta 2 divided by pi r square into t1 to the power of 4 minus t2 to the power of 4. This equation gives the net exchange of heat between the two bodies, not between A1 and A2, between dA1 and dA2, because we considered only the small elementary areas. Okay, now the total net rate, because till now we considered only the dA1 and dA2. Now we need to find what is the total amount of net rate heat exchange between A1 and A2. To find that, we need to integrate the above equation. By integrating from 0 to A1 and 0, because dA1 dA2 are the elementary areas of A1 and A2. To find the total net heat exchange between the two bodies, we need to integrate this particular equation with between the limits 0 to A1 and 0 to A2. This equation number 3 gives the total net rate of heat transfer of energy between the A1 and A2. Okay, by integrating we get what is the amount of heat exchange between the bodies A1 and A2. Here T1 minus T2. Similarly, the amount of heat emitted by the body 1 A1, because in till now we consider dA1 and dA2. Amount of radiation emitted by the body A1 and falling on the body A2 is given by this equation number 4. This equation gives the net exchange of heat between the two bodies. This equation number 4 gives the heat, amount of heat which is emitted by the body 1 and falling on the body 2. Emitted by the body A1 and falling on the body A2. Equation number 4 gives. But from Stefan-Boltzmann law, we are having, for a black body, we are having Q1 equals A1 into sigma T1 to the power of 4. From 4 and 5, Q suffix 1 semicolon 2 gives the heat which is emitted by the body and falling on the body 2. Q suffix 1 gives the total amount of radiation emitted by the body. Are you understanding? All the radiation emitted by the body doesn't falls on body 2. It scatters in all the directions. Q suffix 1 semicolon 2 gives the amount of radiation which is emitted by the body A1 and falling on the body A2. Q suffix 1 gives the radiation emitted by the body A1. The ratio from 4 and 5 we can write Q suffix 1 semicolon 2 divided by Q suffix 1 equals 1 by A1 integral of dA1 dA2 cos theta 1 cos theta 2 by pi r square. Q suffix 1 2 by Q1 is defined, this ratio is defined as the shape factor F12. On the right side we can remove this, we can replace this term by F12, where F12 is known as shape factor, the ratio of amount of radiation which falls on other bodies to the amount of radiation emitted by the body. This ratio is known as shape factor, or it is also called surface factor or wave factor between the two radiating bodies, and is the function of geometry only. F12 is defined as the shape factor. Shape factor is defined as the fraction of radiant energy that is diffused from one surface element and strikes the other surface directly with no intervening reflections. That means the amount of radiation emitted by the one body which falls on other body, all the radiation emitted by the body doesn't falls on other body, it scatters in all the directions. All the radiation emitted by the body 1 doesn't falls on body 2. The ratio of radiation which falls on body 2 to the total amount of radiation emitted by the body 1 is called the shape factor. That means the fraction of energy, the small portion of radiant energy that is diffused from one surface element and strikes the other surface. It is the ratio of radiation which is emitted by the body and falls on other body to the total amount of radiation emitted by the body is called shape factor. F12 here represents, it is the amount of radiation emitted by the body 1 and falling on the body 2. And the heat exchange between the body 1 and 2 is given by the equation F12 into A1 into sigma into T1 to the power of 4, where F12 is the shape factor between 1 and 2. 1 here The first term represents the radiating body. The second term represents the body on which the radiation is falling. Similarly, Q21, where Q21 represents the radiation emitted by the body 2 and falling on the body 1. Q12 represents the radiation emitted by the body 1 and falling on the body 2. Q21 represents the radiation emitted by the body 2 and falling on the body 1. Reverse case. Okay. Similarly, from Stefan-Boltzmann Law, similar to the last case, Q2 equals A2 into sigma 2 to the power of 4. From 8 and 9 we can write Q21 by Q2 equals 1 by A2 into 0 to integral of dA1 dA2 cos theta 1 cos theta 2 by pi r square. This right hand term can be replaced by F21, where F21 is the shape factor of body 2 with respect to 1. 21 represents the radiation emitted by the body 2 and falling on the body 1. I already said the first term represents the body from which the radiation is emitted. The second term represents the body on which the radiation is falling. And Q21 equals F21 into A2 into sigma into T to the power of 4. Gives the amount of radiation emitted by the body 2 and falling on the body 1. F21 into Q2. Okay.